Okay, so let's continue talking about local models on Riemannian manifolds. So we're going to try to construct a quadratic model. It's like on a Riemannian manifold through the use of a retraction. And if you recall, it's like the bottom line, if you will, is that we had a proposition which showed that if you had a sort of a local model, sort of mx, right, that you can show that it's order q, right? Sort of by looking at the error you introduce by replacing f of y by mx at y with some constant. It's like, but normally instead of the distance between x and y, you can express it in terms of retraction. Okay. All right. Okay. So the basic idea then is that with this result, then there's a very natural way, of course, it's like to construct a model, it's like of that order, essentially by using the retraction. Okay. And of course, the way you do this is that you have obviously a map from M to R, which is the function f, right? And you know that you have a retraction, Rx, which maps the tangent space at x to the manifold M. It's like to M, at least locally. Okay, and so it's natural to look at essentially a function here, right, which I call f hat of x, which is essentially the local representative of the function f with respect to this retraction, right? So if you have a retraction like this, then the inverse of the retraction gives you something like a coordinate chart, right? As long as you've chosen a basis for the tangent space at x to m, right? Once you have a sort of a basis for this, then this inverse map, it's like composed with that representation in terms of the basis, gives you an honest to goodness coordinate chart, and then you can look at the local representative with respect to that. Okay, so of course this property is making this diagram commute means that f hat of x is really just sort of Rx composed with f, right? Okay, so we want to look at this object here. Okay. Okay, so essentially this is the pullback of f to txm, okay, through this map Rx. Okay, so all right, and that's oftentimes denoted by the following. It's well, let me write it this way. Okay, so it's Rx star f. Okay, so this is f and the pullback of f by Rx. Okay, so let me just say a little bit about why this is called a pullback. Okay, so you have the function f, right, which is a map from M to R, and you have a map from Txm to M. Okay, so the pullback is something which takes this scalar valued function and pulls it back now to a scalar valued function on Txm. Okay, or more generally some sort of function, right? So it's called a pullback because the map is from Txm to M, right? But you pull this function back, it's like to Txm. So that's sort of what this is. And this is a natural kind of object, and you'll see that, you can just see from the definition that it doesn't rely on this map being invertible. Okay. Anyway, so you can generalize these notions of pullback. It's like to more complicated objects than just scalar valued functions, but certainly applies to this as well. Okay, so in any case, it's like you have now, it's like a function, it's like on Txm, and as we had talked before, we had talked about local models on sort of general Euclidean spaces, and this is of course a general Euclidean space. And so we can construct a model here, right? Through this, we can construct a model on Txm. It's like of f hat of x, right? So what you want to do, or what we can do, right, is construct model of f hat x, okay, on Txm, okay, via sort of what we know of models on sort of general Euclidean spaces. Okay, and actually I had sort of erased it, but let me sort of just write down what I had before, right? We had something like f of x plus the inner product between the gradient of f of x with h, right, plus 1/2 the Hessian. Well, actually, let me just write this as h, right? H, right? Right, so that's essentially what we can do here, right, to f hat of x. Okay. All right. So let mx hat, right, be the order Q Taylor expansion of, well, this is just a quadratic one, but you can obviously do higher order Taylor expansions. Okay, about 0x. Okay. And then once you have that, you can obviously push that back to m, right? And you can finally, you can push mx hat forward. Okay. Through Rx. So the push forward, okay, so this is the push forward, right? The push forward requires this to be invertible, but we have a retraction, so that actually is invertible locally. Okay, so you can actually push this forward to then define an mx that's like on m. Okay. So I'm going to write mx, right, as mx hat composed with Rx inverse. Okay, and again, you need an inverse here, so this is not quite as natural as the pullback, right? So this is the push forward. Okay, but anyway, so then this is, so this model mx, right, is an order Q model of f about the point x on the manifold. Okay. So, and then the obvious model, right? So the obvious quadratic model is the following, right? Okay, mx hat and some vector is equal to fx hat at 0x, right, plus df hat x 0x in this direction, plus 1/2 d squared fx hat 0x. Okay, this is just a Taylor, second order Taylor, f of x plus the gradient of f of x plus 1/2 the Hessian f hat x at 0x. Okay, all right. All right, so here we used some properties. It's like of the retraction, okay. So as before, it's like we have this local rigidity property, right? So local rigidity, which basically means that d of Rx at 0x is the identity. We had already talked about that on Txm, right? So what happens is that d of f of x is d of f hat of x at 0, x, okay? And then this implies that the gradient of f hat at xk of 0x is equal to the gradient of f at xk. All right, so that allows you to have this expression. So the second order, so in practice, this second derivative can be difficult to compute, right? The second order differentials of fx hat, okay, may be difficult to compute. Okay, so the first order differentials are fine because of this rigidity property which we discussed. Because of the local rigidity. So, all right. So what happens, of course, is that if you recall, it's like you know, you can sort of work with things like the covariant derivative instead. It's like in particular the Riemannian connection or the Levi-Civita connection. And the Riemannian connection, it's like has sort of nice formulations when you are on Riemannian submanifolds or Riemannian quotient manifolds. Okay, so recall that we have nice expressions for the Riemannian connection. Blah, blah, right, on Riemannian submanifolds. And Riemannian quotient manifolds. So what that sort of suggests is that it would be nice to deal with this term. It's like using the Riemannian connection instead. Okay. So this suggests the model, which is given as follows. again, mx is equal to m hat x composed with Rx inverse, okay, where now mx hat, right, is equal to f of x plus the gradient f of x, comma, c, right, plus 1/2 the Hessian of f of x, where c is in the tangent space at x to the manifold M, and where the Hessian, right, of f of x c is equal to the gradient, well, sorry, the covariant derivative, it's like in the c direction of the gradient of f of x. So what's the problem? Okay, so the problem obviously is that this depends on the choice of covariant derivative. Okay. Okay. So right. And why is that? It's because I just erased it, unfortunately, but it's like in the expression we had, it's like we had taken the Hessian of f hat, right? And what you've done is to replace that Hessian, it's like with the Hessian of f instead, okay? So that's the problem. So in general, this is only order 1 because the Hessian of f of x in general is not equal to the Hessian of f hat. Okay, x at 0, right? Okay. But recall we had sort of seen sort of an issue like this before when we had talked about Hessians, all right? And if your if your affine connection, it's like had a certain property, which was that it was second order. Let me rephrase that. If the retraction, it's like had the property that it was second order, right? Then you would be okay. So. Okay, so, but recall that if R x is second order, is a second order retraction, then you have the property that the Hessian of f of x actually is equal to the Hessian of f hat x at 0x. Okay. But more importantly, for any retraction, you have that equality at a critical point. Okay. All right. So anyway, so this is just sort of an observation that if you happen to have a second order retraction, it's like then it is much easier to do this computation because you can just look at the covariant derivative. It's like of the gradient of f of x. Okay. All right. All right. Anyhow, but you know, in either case, irrespective of whether or not you have a second order retraction, you still have this equality hold at the critical point, which is important for the convergence results. Okay. All right, so let me just say a little bit more about this. Let me just leave that here for now. All right, so we've been talking about all these quadratic models. It's again what we would like to say is that this is closely related to the geometric Newton method. So the quadratic model right is closely related to the Newton algorithm. Okay, so assuming that the Hessian is non-singular, at x, okay, the critical point C star, right, of this local quadratic model. Sorry. I'm sorry, that's mx. Satisfies the Newton equation. Okay, so if you have that the Hessian is not singular, then this critical point of mx satisfies the Newton equation, which is that the Hessian of f of x plus grad f of x equals to 0. Okay. So all that's basically saying then is that what the geometric Newton algorithm is basically doing, right, is constructing, or one way of interpreting what the geometric Newton method is doing is that it's constructing the next iterate by looking at the critical point of this local quadratic model, right? So the geometric Newton method can be thought of, right, as defining the next iterate as the critical point of the quadratic model. And of course, it's like, you know, the nice thing about working with quadratic models in particular is that it's well understood how you then use trust region ideas. It's like to construct good methods. It's like with global convergence properties, right? So this lends itself naturally to generalizing trust region methods to Riemannian manifolds. Okay. All right, so let me just stop here for now.